Okay, so today we're going to start this habit that we're typically going to have, maybe not every class period, but most class periods, where we split the lecture into two parts. We have a lecture 2A and a lecture 2B. And halfway in between the two lectures, we'll stop the video and you'll take your quiz. I'm doing that for a couple reasons. One is that it helps you to hopefully stay on top of things, that you are, you're really focusing on taking good notes during the lecture, because the quizzes are mostly going to be about the lectures, which is of course related to the reading too. And secondly, since we meet so early, hopefully it'll help you stay awake. Okay, maybe jolt you awake if you're feeling sleepy. So again, we have two lectures today. Again, what I'm doing here is, we've got these first few chapters, chapters 0, 1, and 2, that I'm kind of all doing at once in a sense. Chapter 0, as you've experienced by doing the reading, is very long with a lot of content. Chapter 1 is actually fairly short, introduction to groups. Chapter 2 gets a little longer again, gets into more detail about groups. I'm trying to essentially do them all at once, but the main part of your homework is going to be from chapter 0. So we did that the first day of class on Wednesday. We're doing that still today. We're still going to talk about chapter 0 still on Monday next week. Continuing to sort of also slowly go into chapters 1 and 2, okay, which is again about groups, examples of groups and basic properties. So in lecture 2A, we're going to look at a couple more examples of groups, more algebraic structures. Talk in more depth about functions and sets than we did last time. Talk about something called equivalence relations, which you have read about and done some homework problems about already. Then in lecture 2B, we'll talk about induction, do an example proof using induction, and some foundational number theory. And it's that number theory that's probably the most important part of what we do today. So here are a couple more algebraic structures that we could think about. We looked at last time examples involving sets of numbers. What did we see? We saw the natural numbers. Did the natural numbers form a group? No, they did not. They did have a binary operation of addition. I should have said the natural numbers with the binary operation of addition. What properties of group did they not satisfy? There was not, for example, 0. What did I call 0? 2 words. Additive identity. 0 is not a natural number, so there's not an additive identity in there. There are also not additive inverses. -2, for example, is not a natural number. But then we saw the integers. Did they form a group? Yep, they were our first example of a group. Briefly, we also mentioned that the rational numbers form a group, the real numbers form a group, and the complex numbers all form a group. They satisfy having a binary operation. Addition is what we focused on. You can focus on multiplication, but you do have to make some modifications if you do so. Under addition, they are closed. It's a binary operation, and I said the binary operation, in our book at least, is assumed to be closed when you say a binary operation. You've got associativity, you've got existence of an identity, and you've got existence of inverses, in those cases, additive inverses. Does this set satisfy all those conditions? Let G be the set of all real-valued functions of the following form under the binary operation of function composition. Kind of a strange thing. The operation is function composition. What would happen if we compose two functions of this form, f sub n and f sub m, where n and m are integers? By the way, with function composition, you could put a little circle between them. You may have seen that in the past for function composition, but our book does not make a habit of doing that. It just puts the functions right next to each other, as you saw in your assignment. What does this mean? It means plug one function into the other, go from right to left, really. Plug fm of x into fn. Plug the output of fm into fn. Let's see what happens when we do that. Use the formula that you see here. Fm of x has a formula that it equals, as long as we're not dividing by 0, we're not worrying about domains here. it equals that. Plug that into Fn, what does that mean? It means replace the x right there and right there with that expression, the output of Fm, x over 1 plus m times x. You should have done things like this way back even in pre-calculus. Doesn't look like it's a function of the same form, but we should simplify it. Multiply the top and the bottom by 1 plus m times x and get cancellation. And lo and behold, after simplification, this example special, you get a function of the same kind of form, x over 1 plus some integer times x. So under this binary operation of closure of function composition, it is closed, okay? Again, the author says binary operation automatically means closed, but we really should verify it. In general, a binary operation, again, just means take two things, combine them to get a new thing. Binary meaning two. You can have trinary operations as well, but mostly we do binary operations. So it looks to be closed. Does it satisfy associativity? Well, function composition always satisfies associativity. Let me write that over here. Let's use Greek letters like you have for your homework. You got three functions, alpha, beta, and gamma, defined over appropriate domains. I'm not going to bother writing the domains. What does it mean to say alpha, beta, gamma equals alpha, beta, gamma, where the operation is function composition? Again, over appropriate domains. I'm just not specifying those. But what does this mean? For an arbitrary input, call that input A, it means essentially plug gamma, that function, into this function that you can call alpha beta. It means compute this thing. Emphasis on the alpha and the beta going together. But what does that mean? It means plug the input that you see here into the function that we're calling alpha beta, alpha composed with beta. And what does that mean? It means do this. Just think of this as, we're plugging that thing right there into the function alpha composed with beta. What does that mean? It means do this. Plug it into beta first and then plug it into alpha. And if I write it the other way, emphasis with the parentheses around the beta gamma, what does this mean? It means plug the output of the function that we're calling beta gamma, beta composed with gamma, into alpha. It means do this. Like that. Put the parentheses around the beta gamma inside the input for alpha. But what does that mean? What does it mean to take beta gamma and apply it to A? It means do beta of gamma of A. So many parentheses. But this does give me the same answer I got doing it this way. These are the same for an arbitrary input A. And that means these functions are the same functions because they have equal outputs for an arbitrary input. It's confusing, right? I get confused looking at this kind of thing sometimes too. You got to think very carefully about it. What does function composition mean? This is kind of strange notation. But this is verifying associativity. It's verifying these two functions are the same thing. It's almost too easy in a sense that it gets confusing. And there's so many parentheses. But that really is what's going on. So it satisfies associativity. Does it satisfy commutativity? Function composition in general does not satisfy commutativity. You should remember that from pre-calc and calc. But for this kind of function, with this kind of formula, it would have to. We'd have to, you know, if you did it the other way around, switching around the roles of the n and the m, in the other order, you'd get really the same thing because you'd get an n plus m there. And addition of integers is commutative. So with this example, it happens to be commutative. Existence of an identity? What would be the identity? Is there one? What would be the identity function? Does the set have an identity under composition?
Is it the inverse function?
There are going to be inverses. What function would play the role of the identity under function composition? If there was such a function, what should we call it? Maybe we should call it. Let me go ahead and use the circle here. That's function composition, binary operations. Maybe we should call it ID for identity. What would it mean for ID to be an identity function? It would mean that when I compose ID with an arbitrary function, that I get that arbitrary function back. The operation is function composition. And what does it mean for this function to be the same function as this function? It would mean that the output for an arbitrary input is the same. I'd want this thing to equal that thing, so I want this to equal this. Is that true? I mean, well, what would ID of x need to be to make that true? This is difficult for 7:45 in the morning. ID of x would need to equal x. And that is the identity function. For an arbitrary input, the output is the same. The domain and range have to be the same set. Is there a value of n that will make this equal to x?
0.
Yeah, and a 0. F0 of x is x over 1 plus 0 times x is x. The identity function. And that will serve as the identity of this thing, this set. This set is going to be a group. And what's the inverse? Let's just write it like this, of Fn. If you think about it, it's going to be f sub negative n. But the operation is not addition. The operation is function composition. The elements are not numbers. The elements are functions. This is something to get used to in this class. These functions are related to numbers and integers, but the elements are functions. The operation is function composition. Here's another example. I'm not going to go over this example in detail for time's sake. Oops. Let GL2R, weird, what is that? Be the following set here, where the binary operation is matrix multiplication. GL2R, GL stands for general linear. You don't need to know that for future tests, I'm just informing you now. 2 means it's going to be 2 by 2 matrices. R means the entries of the matrices are going to be real numbers. A, B, C, and D are real numbers. But the objects of this set are 2 by 2 matrices with the additional property that the determinant is non-zero. So the objects of this set are matrices with that property. The operation is matrix multiplication. It's going to satisfy those properties. It will satisfy closure when you multiply 2 matrices, 2 by 2 matrices. You'll get another 2 by 2 matrix. And more importantly, its determinant will stay non-zero. Maybe you remember from linear algebra, the determinant of the product of two matrices is the product of their determinants. That's a fundamental property of determinants. So if these two determinants are non-zero, this one's going to be non-zero. Associativity? Yeah, matrix multiplication is associative. I'm not going to prove that, but that's true. Identity? What do you think the identity is? The identity matrix. We usually call that I. 1, 0, 0, 1. Can you see that? It's too dark. Okay. And such matrices, such non-singular matrices with a non-zero determinant have multiplicative inverses. A inverse will exist. And you can find a formula for it. Maybe you remember that from linear algebra. It is important that this is true so that these matrices are all invertible. That turns out to be a group too. The group concept is very broad. All right, now let's review some things. We'll quickly review modular arithmetic, and then we'll get back to sets, functions, and equivalence relations. This is something you should have written down last time, so let me just do a quick review of it. In this class, Zn always represents this set. And it's always assumed, when you write Zn, that the operation is addition mod n. That's always assumed, unless said otherwise. Okay? So Zn is not just a set, it's a group under the operation of addition mod n, where what that means is you find the remainder when x plus y is divided by n. Do a quick example again. We're talking about, say, Z7. Elements are 0, 1, 2, 3, 4, 5, and 6, not 7. 7 is equivalent to 0, mod 7, but it's not really part of the set. If you want to do, for example, 5 plus 6, you take that number as an ordinary number, 11, and mod by 7. Meaning, find the remainder when you take 11 divided by 7. 11 divided by 7 is, got a remainder of 4, right? This is 4. Mod 7. Usually you put the mod at the very end, and just once typically. 5 plus 6 equals 4, mod 7. 5 plus 6 usually is thought of as being 11. But when you divide 11 by 7, you get a quotient of 1 and a remainder of 4. So 5 plus 6 equals 4, mod 7. 5 plus 6 equals 4 in Z7, in the binary operation of Z7. Okay? This is just a little bit, getting a little bit more technical. Technically speaking, a binary operation takes ordered pairs as input. It's a binary operation and gives you a single thing in the same set as output. And because the codomain is taken to be the same set, that's why we're saying it has closure. At least in our author's point of view. This is abusive notation. I won't typically write this kind of thing. I won't typically write that. I was just doing that to emphasize it's really a function. A binary operation. That's going to be a very important example for us. Perhaps the most important example in the whole course. Z. Perhaps. You can do this kind of stuff, modular arithmetic in Mathematica. This is a new slide. Use mod a comma n inside square brackets to find the remainder when a is divided by n. So if you want to find oh, 114 mod 7. If for some reason you needed to do that. In Mathematica, you type this in as mod capital M square bracket 114 comma comma 7. See if I can do that in my head. What's the remainder when you divide 114 by 7? Well, 7 goes evenly into 70. What's left over? So from 70 would then be 44. 70 plus 44 is 114. So this is going to be the same as doing 44 mod 7, which is a little easier to think about. Seven goes evenly into what? 42. So the remainder would be 2 there. The answer is going to be 2 for that, and it's also going to be 2 for that. Let's go ahead and check it out in Mathematica. Well, before I do that, I want to quickly show you the next line, which you probably don't need to write down. This works even for very big numbers in place of a and n. So I'm not sure what the limits on this capability might be. Let's check it on Mathematica. Go ahead and do mod 114 comma 7. 2. By the way, you might wonder what this is here. That's our mod 2 clock. I made it. Mathematica that we saw last time. And yeah, Mathematica can handle in general very big things for a and n here. We could do mod, for example, of, I don't know, 7 to the 63rd power. Mod, I don't know, 13. 5. Or maybe even mod 1300, 343. Just like that. Okay? Which is theoretically good for applications involving maybe cryptography. You don't need to write this down if you wrote it down last time. Probably even if you didn't write it down last time, because we're going to go on as quickly as we can here to some other stuff. Just reminding you that a function is a rule of assignment. That's really informal. To be more formal and define functions, you actually have to define functions as sets. I don't want to do that. Our book really takes a more informal approach with functions and equivalence relations, for example, as well. When you use this notation, that's taken to be the domain. This is taken to be the codomain. Again, our textbook doesn't use that terminology. I will. Actually, again, earlier editions of the textbook did call it codomain, but that's consistent with your linear algebra book to call it the codomain. I will typically call the set of all outputs the image. That will be the most common the word I use, though some people call it a range. Some people also call the codomain the range, so it gets really confusing that way. I will generally avoid the word range, except for last time and today. One-to-one means that if you've got the inputs being the same, the outputs being the same, then the inputs must have been the same. Equivalently, if the inputs are different, then the outputs are different. Those two statements are equivalent to each other. Onto means for all possible elements of the codomain, there's something in the domain that gets mapped to it. One-to-one and onto functions are called bijections. And functions in such situations are invertible. What does that mean? That came up on your homework. I will talk about it in a minute here. Let's quickly go over some other slides, though. These are new slides. So these are worth writing down, I think. I've already lost my black marker here. Behind. Given non-empty sets A, B, and C and functions phi and psi, okay, many people call that phi instead of phi. It's been my experience that mathematicians tend to call it phi and physicists tend to call it phi. It's never been something that has been contradicted in my experience. I asked a Greek teacher, is it phi or phi? And he said both. Okay. You could call it phi, you could call it phi, just don't call it pho or phone. A to B, this is a psi. Everybody agrees to call this psi. From B to C. When you compose them, you're creating a new function, phi compose psi or just phi psi. by that formula, just as we talked about a few minutes ago. That's the definition of what this means. Okay? There's an implicit binary operation going on here, combining these two functions to get a new function. Oops. Note, the new function, psi phi, goes from A to C. It's common to draw a diagram in this situation. A couple kinds of diagrams. You could draw a diagram like this. And put phi and psi above the arrows, like that. And then the composition goes from A to C. And that composition, careful, puts psi first and phi second. But you know with function composition, you're really going from right to left. When you plug a number or an element in, you first plug it into the function on the right, into phi, then you plug it into psi, just like this equation says. Phi is the inside function and psi is the outside function. So that's one kind of diagram you'll see people make, including me. Sometimes we do Venn kind of diagrams as well, blobs, to represent the sets, and you imagine the functions as being what are called mappings, mapping elements in one set to other sets. Like if you start with an element A there, you get mapped to phi of A here, and that gets mapped to psi of phi of A here. That's a helpful visual sometimes when you think about these things. Got that? I am mostly, before quiz 1 here, before the end of lecture 2A, just reviewing some facts that you should know. Well, maybe we should prove what I'm about to show you. This is worth knowing as one example of how functions and sets, and in particular unions, can combine, so to speak. These are a couple of properties that are true. We got two functions. Well, actually, in this particular property here, we're only focused on the function phi. And A1 and A2 are both subsets of A. I guess I am doing both union and intersection here. Then phi of the union, the image, this is not phi of a particular element. This is phi of a set, meaning it's the image of that set under phi. It's all the possible outputs that you can get by taking inputs from the set and plugging them into phi. That is equal to the union of these two sets. And the image of the intersection is a subset of the intersection of these two sets and not necessarily equal to it. We might wonder why it's not equal. Maybe we should just focus on that second one, as far as proof goes. Again, proofs should be written in complete sentences. When you do your star problems, you should write in complete sentences. However, me in class, I will not always live by that for sake of time. Okay? Can we verify this property, essentially do a proof? In quotes, it's not really going to be a proof because I'm not going to write sentences. But essentially, it's the idea of the proof. How would you do that? How would you prove this? Well, we did talk about this last time. How do you show one set is a subset of the other set? Take an arbitrary element in this set and show it's in that set. So I could say, if I was given an arbitrary element, let me call it B, because it is going to be in the set capital B. Take an arbitrary element in this set, and again, this is a set. I'm not plugging one particular element into phi here. I'm thinking about all the possible outputs that I could get by plugging all the elements in this set into phi. What does that mean to be in this set? It means there's something in this intersection that gets mapped to B. This implies there exists some element of this intersection such that I will almost always abbreviate such that ST. Though maybe just this one time I will tell you that some mathematicians abbreviate such that with a backwards kind of. But I will almost never do that. So I will just do ST for such that, and you can use that abbreviation as well. That's what it means for B to be an element of the set. A is in the intersection of A1 and A2. What does that mean? Do it this way. This implies what about A? Can you finish it for me? A is in the intersection if and only if.
It's in both.
It's in both of them. Emphasis on the word and. If it's in the union, it would be in one or the other, or both. But A being in both A1 and A2 means really B is in both of these sets. And so it's in their intersection. Done. This is in the image of A1. Can you see it okay here? And B is in the image of A2. And for sake of time, that I will not write it down. That means B is in here, the intersection of those two things, and therefore this is a subset of that. For sake of time, I'm not going to try to explain why it's not equals, why this is not a subset of that in general. But I would encourage you to think about it on your own, and think about if there's any extra assumption you can make to make equality there. Maybe phi needs to be onto or one-to-one. That can make them equal. As you saw in your assignment, you've got these facts. That was in your assignment. Close to quiz time here. And those are facts you should remember for the future. Right? You prove these things. Here's something that you did not prove. In the last situation, when everything's a bijection, one-to-one and onto, the inverse function of the composition psi phi is the composition of the inverses in the opposite order. That can make sense if you think about the picture. Redraw it over here. Picture, of course, is not a proof, but C phi psi. Probably didn't need to draw the blobs. Yeah, I didn't need to. The function psi phi is what goes from A to C. Its inverse function would have to go backwards the other way. This would be psi phi inverse. If you're going to take it in steps, it should make some intuitive sense that you'd have to apply inverse psi first before inverse phi. And that's what this notation is saying. Apply inverse psi, the inverse of psi first before you apply the inverse of phi. All right, I wanted to get to equivalence relations before the quiz, but I think we can stop, take the quiz here.